Hi, this the last section of chapter 15. It is talking about the second law of thermodynamics. And the main topic here, we are going to start talking about heat engines. And this is the engine here. It is extracting heat, an amount of heat called Q hot from a reservoir that is at T high, and expelling some of that Q cold at a temperature Tc, and the output of it is doing work, and the work is W. It's an output. Ideally, if we don't have losses, that work done, it is Q hot minus Q cold. It is more, I would say, common to talk about efficiency, which is always output output divided by input. And here for the output, it was Q hot minus QC, and the input was Q hot. I can manipulate this as efficiency Q hot over Q hot minus Q cold over Q hot, and then the efficiency is going to be written as this. Now you can see here that efficiency cannot be 1, unless QC over Q hot equals 0. And then always it is less than 1, or we will say, most of the time we will express efficiency in percents, and therefore it is less than 100%. Okay, but there was a scientist, his name was Carnot, was able to say, let's assume we have a perfect heat engine, and that perfect heat engine, it is called Carnot engine, and Carnot cycle, it is the cycle that has the most efficient processes available, and the efficiency here is going to be expressed in temperature rather than expressed in terms of quantities of heat. Then the efficiency for Carnot only is going to be 1 minus Tc over dt, and this is the maximum efficiency that we're going to get for a heat engine. Then we don't have any engine in actual life that has more efficiency than the Carnot one. Let's work here with this question. A cyclical heat engine operating between temperatures 450 and 150 degrees Celsius produces 4 megajoules of work on a heat transfer of 5.00 megajoule into the engine. How much heat transfer occurs to the environment? B, what is unreasonable about the engine? C, which premise is unreasonable? Now, in order to calculate what is really the efficiency, I need to calculate first what is the work done. It is Q hot minus QC, and then QC can be calculated as Q hot minus W. The work was given, and also the heat transfer was given. Then I will be able to calculate the first part, which was talking about calculating the Q cold, because it is asking about how much heat transfer occurs to the environment. Now, to calculate the efficiency, we said it is W, the work done, divided by Q hot, which is 4, it's not 400, it is 4.00 megajoule divided by 5 megajoule, then it is 0.8, which means like an 80% of efficiency. Now, if we calculate the Carnot engine efficiency for this, like we can write it this way, we can write it 1 minus Tc over Ts, find that the efficiency, it is 0.415, which is less than the efficiency of the engine. Now, remember we said no engine can exceed the efficiency of Carnot. Okay, then this is what is unreasonable about this problem. Here, how much heat transfer occurs to the environment by an electrical power station that uses 1.25 10 to the 14 joule of heat transfer into the engine with an efficiency of 42%. What is the ratio of heat transfer to the environment to the work output, and how much work is done? Now we know that the efficiency, it is 1 minus Q hot over Q cold over Q hot. Then we can rewrite this equation so that we will be able to calculate a Q cold, which is going to be 1 minus efficiency times the Q hot. Whenever we are going to use the efficiency in an equation, it should be in units, or it should be converted into decimals. Then here 1 minus 0.420 times 1.25 10 to the 14, and then this is going to be the answer for A, which is how much heat transfer occurs to the environment, which is Q cold. What is the ratio of heat transfer to the environment to the work output? We want to find Q cold over W, and this was 1.38. Finally, how much work is done? W is Q hot minus QC, and then this is the amount of work that was done. This is just practicing the equation. A certain gasoline engine has an efficiency of 30%. What would the hot reservoir temperature be for a Carnot engine having that efficiency if it operates with cold reservoir temperature of 200? Remember here, temperatures, they should be converted into what? Into Kelvin, and therefore we're gonna add 273. Then this is 374 Kelvin. Okay, and of course we know that the efficiency for Carnot, it is 1 minus TC over TH, and then I need TH, it is gonna be TC over 1 minus efficiency. And finally I will plug in my numbers. Just here I want to show you maybe how to do this, like algebra here. E, which is the efficiency, equals 1 minus TC over TH. I can get rid of the 1, or I can bring this here, 1 minus E efficiency, and this is T cold over T hot. I am looking for T hot, then it's gonna be T cold over 1 minus E efficiency. Okay, just to show you how to manipulate these. Now something opposite to the heat engine, it is called heat pumps and refrigerators. And these heat pumps, they compress cold ambient air, and in so doing heat to the room temperature without violation of conservation principles. Then it's a machine that is going to do the reverse of the heat engine. Now here we don't call it efficiency, we call it coefficient of performance. And when I write here HP, this is heat pump. It's Q hot divided by W. A refrigerator is a heat pump that it takes warm ambient air and expand it to chill it, to make it like colder. And again, we're gonna have the same idea. What is the coefficient of performance of an ideal heat pump that has heat transfer from a cold temperature of negative 25 to a hot temperature of 40? Remember the temperatures here, we need to have them all in Kelvin. Um, Remember the same way that we did with the Carnot engine, we did here, and we did calculate that 1 over the efficiency is going to be T hot over T hot minus T cold. And then 313 Kelvin divided by 313 minus 248 Kelvin is going to be 4.82. Show that the coefficients of performance of refrigerators and heat pump are related by coefficient of refrigerator equal coefficient of performance of heat pump minus 1. Okay, this is Q hot minus Q cold equal W. And then I divided all the equation by W. Then this is Q hot divided by W. This is Q cold divided by W. When you divide W by W, it is 1. I know that Q hot over W, it is the coefficient of performance of a heat pump. And I know that Q cold over W, it is the coefficient of performance of a refrigerator. Okay, therefore, I'm going to substitute these here. Then coefficient of performance of a heat pump minus coefficient of performance of a refrigerator equal 1, and then I will be able to get the relation that the question was asking about. The last topic here, it is entropy, which is, I will say, the loss of energy available to do work. And I will say entropy also can be a measure of randomness or chaos in substance. The second law of thermodynamics states that the total entropy of a system either increases or remains constant. It will never decrease. I'm sorry. The change in entropy can be measured by Q, the heat, divided by the T, temperature, which is the absolute temperature or temperature in kelvins. On a hot summer day, 4.0010 to the 6 joule of heat transfer into a parked car takes place, increasing the temperature from 35 to 45. What is the increase in entropy of the car due to this heat transfer? The change in entropy is Q over T, and actually this temperature here, it is the average. If you will have this 36, sorry, let's do the calculation here just to show you. If we will 35 plus 273, it is 308. And 45, it is 318. And then when you add 318 to 308, you divide by 2, then this is 313. Okay, and this one here, it's not joules, this one, it is Kelvin. Then this was times 2, 626. When you divide by 2, you're gonna get 313. What is the decrease in entropy of a 25 grams of water that condenses on a bathroom mirror at a temperature of 35? Assuming no change in temperature and given that the latent heat of evaporation to be 2450 kilojoules per kilogram. The change in the entropy is going to be Q over T and equals in the same time the amount of heat that is lost due to evaporation, due to condensation, because when the material is going to condense, it's going to lose this amount of heat, which is M times LV, and then divide by T, which is in which is in Kelvin. Okay. Thank you.